that I gave at Butler in the fall. So I titled it, I was trying to think of, okay, how do I kind of combine all of this sort of weird, unusual nuclear physics stuff that even, most physicists don't spend any time thinking about into a single title. So I ended up lumping it in as particle zoo, which is something that we've talked about a bit, all these different types of bound states of quarks and gluons. Melted nuclei, which is the area that I do research in, and then frozen stars, which is sort of a poetic name for neutron stars and other related type possible objects. Okay, so this is what we've talked about before, that we're mostly made of atomic matter. The electrons don't really matter for much, so we just ignore them whenever we're talking about nuclear physics, or when we're talking about particle physics. I'll use the term QCD, quantum chromodynamics, to talk about the strong nuclear force. So the electrons are so far away, they don't matter. The quark mass, as we learned from the video, saying that most of the matter, or most of the mass of atomic matter, does not come from the Higgs mechanism. We have the quark mass, we can remember it accounts for only about 1% of the mass of a proton, for example. So then, okay, so there's the picture of the gluons as being like little springs connecting the quarks together. But if you remember from that video where he was digging in the sand on the beach, talking about flux tubes, they don't really connect like that. It's more like a Y shape in the middle. But even going beyond that is really much messier, and the interaction energy, which we can think of as gluons just spontaneously turning into quark anti-quark pairs throughout, so you can kind of see that in the picture. That's the interaction energy, and that accounts for about 99% of all mass of ordinary atomic matter. Okay, so what do we know about this force, the strong nuclear force? So here's there's lots of these little cutesy illustrations of particles that you can find on the internet. And so here's the 6 flavors of quarks that we've talked about, up and down being the ones that are present as valence quarks in ordinary nuclear matter, so like protons and neutrons, or even so we talked about how they exchange virtual mesons. Those are still mostly going to be made of the up and down quarks, like pions and rhos. Then we sometimes group the strange quark in as a third flavor of light quark. Because they're not that much more massive, so even at relatively low energies, we still have to include those. And then charm and bottom can be produced in some of these cases, but the top quark is really only produced in really high energy. And then they're all bound together by gluons, being the force particle for the strong nuclear force. Okay, so we've got 2 sort of regimes or energy scales and length scales that we have to think about when we're talking about the strong nuclear force. So we have confinement, which we talked about as being a strong interaction. So this picture here is taken from a paper on lattice QCD. So that's trying to solve the strong nuclear force directly using supercomputers, and they can do so in certain limited cases. My internet connection is unstable. Are we still good? Everybody hearing me? Yes? No? No, I'm cutting out. Okay.
It's a little shaky.
Yeah, it's a little bit.
You cut in and out.
Well, that's not great. Of course, day one of trying to do this, my wife has a Zoom thing going on at the exact same time as our class. So is it better now?
Yeah.
Okay. All right.
Yep.
Yeah. Okay. So we talked about confinement, right? That you can't get a quark by itself. So this picture from lattice QCD, direct solution using supercomputing resources, but can't apply to all situations. in particular, you can't like use it to calculate the mass of the proton just from first, from basic principles. So this applies at low energy, large distance. So then on the other side, when we talked about, I've used this cartoon in class before spring break, or before social distancing, where, so this is an electron that is being shot into a proton. And so at really high energy, really high momentum, we can treat when the quarks are close together, they are barely interacting at all. So they're almost acting like free particles. So this is what's happening at particle colliders like the LHC. And this can be solved exactly. And so I'll call that easy. Now, easy, being really in quotes, like, okay, you can get a PhD and learn how to do these calculations. That's what I might mean by easy, as opposed to in the low energy regime where you have to worry about confinement. That's hard, meaning that you have to be a supercomputer to even try and do some of them. Or you can try and make up some sort of new theory so you don't have to do things directly, but sort of a new mathematical approach. And that's kind of the area that I work in, and we'll talk about that a bit later. So okay, here's everything sort of on one big picture, the nuclear phase diagram, right? And we'll talk a bit about phase diagrams later when we get a bit more into the details here. But we've all probably seen, in chemistry, or even, like high school chemistry, you would have seen a phase diagram about, we're familiar with water, right? At certain temperatures, water is a solid, and at certain temperatures, it's a liquid, and then it's a gas. But where that boiling point or that freezing point is varies depending on the pressure as well, right? So if you have really high pressure, then the boiling point, the temperature that it takes to boil water goes up, right? That's the principle behind a pressure cooker. And if you have low pressure, like if you're at high altitude in like Denver or Mexico City, then water boils at a measurably lower temperature. And so like if you're gonna, boil an egg, you have to leave it in the water longer when you're at high altitude. So we have a very similar sort of idea here with nuclear matter, except here, rather than temperature versus pressure, we have more like temperature on one axis and density on the other. So we live basically at the 0, 0 in terms of this picture, because this temperature, this cross, where you can see that that line that bends over at the low density point, that's about 1 trillion degrees, right? So if that's the scale of 1 trillion degrees, then we're basically at 0. And when I talk about density, really you have to take the amount of matter minus the amount of antimatter. So we're not at 0 density, we're at something that's positive, because there's more matter than antimatter around us all the time. So that's why you can see nuclei, like if you get actually within the nucleus, they're very dense, right? So there's a high density there, but it's still low temperature. A particle gas exists at high temperature and low density, but not too high of a temperature. So there you're just producing lots of mesons and lots of other random particles, like in a particle collision. If you get to high temperature and high density, we get a liquid-like phase, which we'll talk about next, which is the quark gluon plasma. Low temperature and low density, that's the early universe, because in the Big Bang, basically equal amounts of matter and antimatter were created. And so you can say that that's basically 0 density, because you subtract those together. And then the neutron stars are at a high density, but relatively cold. And when I say cold, they're like 10,000 degrees or something like that. So like you wouldn't want to like live there. Also the gravity the surface gravity is really high, so you also don't want to live there for that reason. But much cooler than the quark gluon plasma at trillions of degrees. Okay, so that's sort of the big picture. So in this particle gas, okay, there's the hadrons that we're familiar with, baryons and mesons. So I won't spend too much time on that. And the particle zoo that we've kind of gone through. So the one on the right, I showed in class, right, where we had the particles that are spin 0 that can be made out of up, down, and strange quarks, right? So you have the pions, you have the kaons. On the left, we only looked at, let's see, where is the, okay, so you can see the proton and the neutron in the lower sort of back part of the plane, right? So this, that was, if you look at the lower part, that's where you have up, down, and strange quarks that can be made into baryons, right? So we had the Xi particles, the sigma particles, and the proton and the neutron. But then if you start to include charm, you get even a bigger zoo, right? So the vertical axis is adding more and more charm quarks to these baryons. And then you can see if you wanted to include bottom, let alone top, you'd need more than 3 axes. So, you know, people don't even really try and plot those. But, you know, all those combinations of things can be put into this, what we call the quark model, right? It's just either combinations of 3 quarks and it's a baryon, or combinations of a quark and an antiquark and it's a meson. But lately, people have been, experiments have been discovering left and right these exotic hadrons. So these are things that can't be described either as a baryon or a meson. So there's tetraquarks. So I would say probably about 2012, the tetraquark was confirmed. And so a tetraquark is going to be 2 quarks and 2 antiquarks, right, for a total of 4. You can also have pentaquarks. Those were confirmed just like in the past year or 2 at the LHC. Pentaquarks would be 4 quarks and an antiquark. And the thing that is hard to figure out is whether you've truly created a new bound state with that number of quarks, or whether it's more like a molecule, in the sense of, so a tetraquark could be 2 quarks and 2 antiquarks that form a single bound state, or it could be 2 mesons that just happen to be produced close to each other and aren't really a new bound state. There's just 2 mesons that were near each other and sort of interacting like a molecule. So there has been some evidence for some of these that you can really say, okay, at least this one is a tetraquark and this one's a pentaquark, but some of the other ones that look like they might be that might actually just turn out to be molecules more than a new bound state. And then we have even weirder stuff like glue balls. So, you know, physicists love these. Well, I don't know. Physicists used to be bad at naming stuff, but then physicists started taking drugs in like the 70s. And so that's where you get gluons and quarks and, you know, strange and top and truth and beauty and whatever. So that's kind of persisted now. So now we have glue balls, right? So if gluons can interact with each other directly, which they can, then why can't you have a particle where it's mostly just made out of gluons? So this is hypothesized. The difficulty with measuring glue balls is that experimentally they look a lot like regular mesons. So it's hard to determine whether you've made a glue ball or whether it's just a meson. But there's ongoing experiments to try and determine that. And then there's other things that are just called hybrids for now because they don't fit in the quark picture at all. You can't really say, you know, if you just try and make up combinations of things and excited energy levels and stuff, they don't fit. And so maybe there's a combination of, you know, it's quarks and gluons being valence particles rather than just what's binding things together. But at this point, you know, more research is needed to kind of confirm the properties of those and see how they fit within the quark model. All right, so that's kind of it with the particle zoo. So a little bit of review and then some of these new weird things. Any questions at this point? All right, so let's go back to our phase diagram, and now we'll go a little bit more exotic than that, which is the quark gluon plasma. So I often refer to this as melting the nucleus. Right. So how would we melt the nucleus? Well, so on the left picture here, we have a picture of the nucleus. So each of these sort of silver balls or orbs you can think of as a proton or a neutron. And within there, you can see the colored balls, which are supposed to represent the quarks and gluons. Right, so the bigger ones are the valence quarks, right? So 2 ups and a down for a proton, 2 downs and an up for a neutron. And then you have all the sea of particle, antiparticle stuff that gets created. But each of those belong, even though they're all interacting in a nucleus, each of those quarks can be said, okay, this quark belongs to that proton or that neutron, right? They're not shared, and they're certainly not free. But if we could take that nucleus and somehow squish it together, then we could get this point where those silvery orbs start to overlap. And now if I look at, one of those quarks, I can't say which one it belongs to, right? So we call this a deconfined state. So we have confinement, which says the quarks can never be found on their own. This is not finding quarks on their own. It's just that they don't belong to a particular particle. So we call this a plasma, sort of in analogy to what an actual plasma is, right? An actual plasma is a gas that gets really hot, and so hot that the electrons no longer belong to a particular atom, right? So you have nuclei and you have unstable connection. Am I all right? Yeah, no? Am I back? Okay.
Yeah, you're back.
Okay.
Are you just
Okay.
disconnecting? Oh,
Yeah, it's popping up a little warning that says my internet connection is unstable. That's happened twice now. But okay, appear to be good now. So in a plasma you have you have nuclei and you have electrons, and they're all just sort of freely moving around, right? So like in a star or in a fluorescent light bulb, you have the plasma like that. So this is similar in the sense that now it's a quark gluon plasma, right? So you have quarks and you have gluons, but they no longer belong to a particular proton or neutron. So how do we make this, right? You can't just take a nucleus and actually just squish it by hand or like with pliers or something like that. There's no way to apply that amount of force. So the way that it's done experimentally is in heavy ion collisions. So you take a lead or a gold ion, strip it, so stripped of all the electrons, accelerate it in a particle accelerator, and collide them together. So that's what this picture here is showing. They collide, and then they're not always going to be head-on collisions. So you get a hot, dense fireball of nuclear matter in the part where the collision happens, and the other part just gets ripped apart and moves off. Like I said, it's 1 trillion degrees, give or take. And when you say 1 trillion degrees, it doesn't matter what scale you use because it's all about 1 trillion degrees, Kelvin, Celsius, Fahrenheit. And then that fireball is going to expand and cool really rapidly in about a femtosecond. And all those quarks and gluons then, when it gets below that threshold temperature, they're going to join up, right? So this little pocket of quarks and gluons becomes a proton, and this little pocket of quarks and gluons becomes a kaon, and this pions, and you just get stuff flying out, freezing out, and you detect it with a particle detector. So there is some of this heavy ion collision research is done at the LHC, but the more important lab where this is done is the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven. So this is a satellite image of Long Island, and you can see there in the picture, there's a little ring there that the arrow is pointing at. So this is a false color image, but that's the accelerator tunnel there for scale. So if we zoom in, this is an aerial picture there, so you can see like a smokestack and the buildings there. I don't remember the stats, but it's big, right? If you want to go from the star, so these the detectors there are labeled star and Phoenix. If you want to go from one to another, you know, unless you've got a while that you just want to enjoy the outdoors, you're going to drive from one to the other, right? This is a big complex. We can also see there, it's a multi-stage, like we talked about, right? So you start with in the red where it says LINAC, that means linear accelerator, right? So that's where you get you generate the ions and then you use a linear accelerator to speed them up initially, and then we get a booster, and then one accelerator ring, and then it gets injected into the big accelerator rings where they're going around in opposite directions, and then they're forced to collide at those detector bays. So here's the pictures of the star and Phoenix detectors, and I don't know which is which, but they're both about the same size. They're just, you know, they got different designs and different abilities. So, you know, one is better at certain measurements than the other. So they kind of complement each other in that way. But you can see the people there for scale, right? So that's with, you know, partially disassembled. You can also see how complex they are, right? All these layers of tracking and measuring energy that's deposited and stuff like that. So here's, go ahead.
Have you been there before? Like, have you been to Collider before?
Yes, I've been to Rick. So when I was in grad school, Rick is at Brookhaven, which is a Department of Energy lab. And when I was in grad school, I was on a fellowship from the Department of Energy. So we had meetings at various labs 3 different summers. So one year it was at Brookhaven, and yeah, I think I went to Phoenix. It was partially disassembled at the time, so I was able to see inside of it. So it was pretty cool. Phoenix right now is the bay is empty because they're working on an upgrade to the detector, so they've completely disassembled it. So this is a little bit of an animation of. So you got the ions coming in, they collide, and then just tons of stuff flying out, and all of the detectors that get lit up. So that's just a ton of data. I think that's just a replay. A ton of data. So this is from a single collision and sliced, you know, 2D. So like the beam would be going towards you or away from you in this. And so each of those lines represents a track of a different type of charged particle. So you can see some of them are bent, right? Because those, bad internet connection. All right, I think I'm back. So the ones that are bent, right, those are going to probably be because they're lower momentum, right? So they're not going to, they're going to bend more as they travel through the magnetic field, as opposed to the ones that are high momentum and are going to go pretty much straight out. So there's a ton of data here that has to be analyzed for every collision. And this is just a slice of it. It's much more than even is happening at the LHC when they collide protons, at least for each collision. So okay, so what's the quark gluon plasma like? What are the features of it? Well, for one thing, this was the big surprising thing about it, because originally when they started these experiments, they were like, well, yeah, we'll make this sort of, they thought it would be more like a free gas of quarks and gluons. But it turns out that it's more liquid-like, right? So it's strongly interacting. And so whenever you have like a head-on collision between hadrons, if you have a lot of energy, you're going to produce lots of particles, right? And as they go away from each other because of confinement, right? As they go away from each other, you put more energy in there, and then you produce another quark-antiquark pair, right? And then as that continues, you're just going to get jets, they're called jets, but they're big streams of particles made out of quarks that are going in opposite directions. So if you happen to produce a jet, you know, there's going to be hard collisions between quarks that happen when you have these heavy ion collisions. So if you happen to produce one that's near the edge of that fireball, well, then one side of that jet is just going to go straight out to the detectors, but the other one would have to go through the plasma to reach the detectors. But we mostly don't see that other one because it's trying to get through a strongly interacting liquid. So that was the evidence. This is called jet suppression, that we don't see that back-to-back jet and that's the evidence that it's a strongly interacting medium. So that tells us there's a strong interaction, so we're going to have to worry about confinement. It's not going to be easy, quote unquote easy, like the proton-proton collisions. It also turns out to be what we call basically a perfect fluid. So we get collective flow like a liquid. So if in this picture, you can see it's like two spheres. When two spheres collide, if they don't line up perfectly, which there's no way to make them line up perfectly, so you get all, you get some misses, you get some glancing blows, you get some that are close to head on. But if you have this overlap region, it's going to be sort of almond shaped or pill shaped, right? So if you have this sort of almond shaped overlap region, if that was a gas, the stuff would just expand in all directions, right? If you pop a balloon that's not perfectly round, when the air comes out, it just goes equally in all directions. But if you have a drop of water that's like this, well, it's going to flow this way, right? So if it starts to flow this way and then freezes out, you'll see more particles that move out in this direction, in the horizontal direction, versus in the vertical direction on that picture. So that's the evidence for flow, and that was also surprising. So it was surprising that it's strongly interacting and surprising that it flowed like a liquid. But it flows with a very low viscosity, and this is also evidence of strong interaction. So it flows with very low viscosity, like water, except even less viscous than water, as opposed to something like honey. And so it approaches what appears to be a theoretical minimum. There's some theory that predicts that you can't actually have zero viscosity fluids, but this approaches the smallest possible viscosity. A newer result that shows another extreme measurement is that it's the most vortical fluid. So the way I put that is the swirliest fluid ever observed. What can you compare it to? Something very swirly that we're more familiar with. It's like a tornado. So it swirls 1 billion times faster than a tornado. And this was a recent discovery, first published in 2017. Okay. Any questions about the? Yeah.
Does the core gluon fluid, does it carry heat like yeah, like does it carry heat?
So there's transport, meaning
Transport heat,
it
yeah.
does move things from place to place.
Okay.
And there's good evidence that it has time to become thermalized, right? It's not going to start all at the same temperature, but it does start to, the temperature within the fluid does stabilize, right? So like you have sort of a heat flow from the hotter region to the cooler region. But it's so small, right? It's smaller than a nucleus, and it only lives for a femtosecond. So it doesn't like carry heat elsewhere. It would if it could exist, right? It would be, carry heat just like anything else, any other fluid. But because its life is so short, we can only talk about transfer, carrying heat or other sort of transport properties within that fluid. So, but that is something that people try and measure, is the transport properties of it, and try to understand it better, measure or calculate.
So how can you deliver energy inside, like to break that bond, let's say?
To break the bond in the
gluon,
nucleus.
the core gluon bond, or like
So
interaction.
yeah, so it's just that well, so when you collide the nuclei, right, there's just a lot of energy that's from that collision, right? These are collided at like 500 MeV per nucleon, right? So if you think about lead with like what 90 nucleons, right? So there's a lot of energy in each nucleus, and so just that energy of the collision is what creates, takes it from this phase of nucleus to the phase of quark gluon plasma. But it's not like Yeah. So it's kind of like if you think about taking ice and melting it, right? It's different from smashing. Like you could smash an ice cube with a hammer, right? And you're breaking some hydrogen bonds there, right? But you're mostly just making pieces of ice in that case, right? But if you heat it up, then you change that phase. So we're doing more of the heating it up type thing than the smashing things apart. Does that make sense? Or answer your question? Yeah. Okay. All right. So let's now go to a different. Oh, and were there any other questions? All right. So let's go to a different segment of the phase diagram, which was my background. So neutron stars. Right. So this is for scale. I like this picture, even though I mean I've been to Vancouver. Maybe this was made for the meeting that I went to that was in Vancouver. Of Nuclear Physics Society. But maybe more familiar is here's downtown Chicago. So neutron stars are one to two times as massive as the sun, but only about the size of a city. So about 10 kilometers radius or diameter, whatever. And then, okay, so I actually wrote here 1 million degrees is what we're considering cold here. So 100,000 to 1 million degrees. It's also a very extreme state. A spoonful of neutron star material would have the mass of Mount Everest, right? So that's another way to put, okay, so you got a sun that's the size of Chicago, or you've got a spoonful of stuff that weighs as much as a big mountain, right? So neutron star occurs when a massive star dies but isn't massive enough to collapse all the way into a black hole. So as the star, so when the star dies, it's because it doesn't, it kind of runs out of nuclei that it can still fuse. And so then, that fusion was providing heat that kept it expanded and kept gravity from collapsing it all the way. So then when that fusion's gone, it starts to collapse more and more. Eventually then there's nothing to prevent, you have electrons, protons, and neutrons. Those protons start capturing the electrons, right? So we have an electron capture process at a much larger scale than just the, take-home exam that you did in a previous life, it feels like. So you have basically all of the, an electrically neutral star. So basically the same number of protons and electrons. So all those protons are capturing an electron and becoming neutrons. They'll give off a ton of neutrinos, so we can actually detect that if it's close enough with our neutrino detectors. Hasn't happened yet, close enough, but near enough by, but hopefully it'll happen again. So you get that collapse, you get the, so that's, if it stopped there, it will become a white dwarf. Well, if it stopped before we turned all of the protons into neutrons. But if basically all of the protons become neutrons, then you get a neutron star, right? So the outer crust is not that high density, so you're still going to have some atomic nuclei there. You have like, forget if I have no, I don't have the other picture. An outer crust or an ocean of liquid oxygen, I think it is, that's like 1/10 of a centimeter all the way around. And then you have like a centimeter of solid nitrogen, and then, down and down, and eventually you get heavier atomic nuclei. And then you're going to have this place where you have, well, we don't know. Right, so we think that there is mostly like a big ball of neutrons, but this is all from models. So it's possible that maybe at a certain point, if it's so dense, right, the force of gravity is so dense that that some of those protons or neutrons would rather, or some of those up and down quarks would prefer to change to strange quarks, right? So maybe there are lots of strange quarks that happen there. if they're more stable, but we don't actually know that. What we need to know is what's called the equation of state. So the equation of state that we all know about is the ideal gas law, right? So basically you can think of like, okay, the ideal gas law tells us how, if we know the temperature, you know, what's the temperature and pressure, how much volume would we have, right? So if we want to know a similar thing about nuclear matter, right? If we have a certain temperature and pressure, what volume would that star exist in? And so this analogy to tofu, see, this is why international exchange in science is good, because a meeting I went to, every once in a while we have our nuclear physics meeting in Hawaii, because it's not just because we want to go to Hawaii, it's because it's halfway to Japan. At least that's our excuse. So Japan comes and they give their talk. So this was a talk given by a Japanese nuclear physicist, and he said, okay, you know, if you know about tofu, you know, if you have extra firm tofu, you can make a really big block and it won't crumble. But if you have the softer tofu, you can't make the block as big or it'll start to crumble, right? So if you we want to know the same thing about nuclear matter. You know, maybe some of the less massive neutron stars are really just neutrons, but if they're more massive, then maybe there's enough gravitational pressure that makes them collapse and turn into strange matter. And we do know that if it's massive enough, it's not going to be stiff enough to prevent that collapse, and it'll collapse into a black hole. Right. So the question that we don't know is how stiff is the nuclear matter. You know, people are trying to make predictions theoretically, but we don't have good observations. One observation we have is just say, okay, can we explain this mass gap? So this is, I like the name of this, masses in the stellar graveyard. So we have at high mass, those are all black holes, right? So it says LIGO, Virgo black holes. Those are the black holes that we've observed in with gravitational waves. So mergers of smaller black holes to make a bigger black hole. So those are relatively big black holes. And then we see some smaller black holes. It says EM black holes. Those are ones that we've detected with regular telescopes, electromagnetic detection, right? So with X-rays or radio waves. But you don't see any black holes smaller than about 5 solar masses. And you don't see any neutron stars bigger than about 2 solar masses. So why is there that gap, right? What would be in between? Would it be a neutron star, or would it be a black hole, or is there some reason that we can explain why there can't be anything in between? That's one, you know, trying to explain what's already been observed there. But another thing that you can see there, if you look in the neutron stars, there's those 2 that are orange, the LIGO, Virgo neutron stars. So that was the neutron star merger that was recently observed. Oh, I don't know, 2018, I think, late 2018. So they've seen multiple mergers of 2 black holes, but now we've seen a merger of 2 neutron stars. So what happened to those neutron stars after they merged? What did they produce? Did they produce something that's in the middle of that mass gap? Did they produce a neutron star? Was it a black hole? So if we look at these neutron star mergers, which as we know from when we talked about where the heavier elements came from, we know that there has to be a lot of these, even though we've only detected one. I think there's been a second and third since that plot was made, but only a couple so far. Well, now when we see these neutron stars merge, right, they're a little bit more active, right? Because normally we can't see what's going on inside of the neutron star, but as they crush into each other and form a new neutron star, maybe we'll get some observations from this that'll tell us a bit more about what's going on inside of the neutron stars, and it'll help us answer that question about the nuclear equation of state. So this is what's now called multimessager astronomy, where we can look at the same event through multiple ways, gravitational waves, optically, gamma rays, X-rays, well, mostly gamma rays for this sort of collision, neutron star merger. So having multiple ways to look at it is going to be able to allow a better understanding for what's happening, rather than just only having gravitational waves or only having electromagnetic radiation. All right, so this is the origin of the elements that we talked about, and how we see the orange. The orange is the merging neutron stars, right? So that's why we know it's fairly common, because we know that it has to be responsible for a lot of these heavy elements that exist in the universe. All right, questions about neutron stars? All right. Yeah. So in the last few minutes here, I just kind of want to talk a little bit. Won't go through all of this, about one way to try to understand this, these phases of nuclear matter, which is the type of theory that I work on. So this is called a holographic duality, which uses an extra dimension. So a duality, the idea is that you have the same physics that's described with two different types of math. And so the hope is, the only reason why you'd invent new math to do the same physics that you were already trying to do, is if you had a hard problem that you couldn't do with the other math, then you might invent a new math that explains the same physics but is easier to do. So in this case, what's the problem? Well, when we're talking about the confinement scale with QCD, which is anytime you have a strong interaction. So whether you're talking about the particle zoo, what are the energy levels of those states, or whether you're looking at the quark gluon plasma, or whether you're looking at neutron stars, you're dealing with strong interactions. So if we can translate that into a mathematical model where those strong interactions are weak, then we'd be in much better shape. So one example where a lot of work has been done here is trying to write the strong nuclear force in terms of a gravity theory that's in 5 dimensions. And when I say gravity theory, it really means general relativity. So in these sorts of models, we have sort of a dictionary, right? So what we're really trying to do on the left is the 4D particle field theory, which is strongly coupled, which has particles, and which should be the strong nuclear force. We don't know it exactly, though. On the right side, we'd have a 5-dimensional gravity in curved space. So that strongly coupled particle theory would become a weakly coupled gravity theory. What we describe as particles now are gravitational fields. And the whole game is to try and somehow either derive or guess what that 5D theory of gravity should look like that would describe the same thing as the strong nuclear force. So putting it in meme form, why don't we take all our strongly coupled nuclear physics problems and push them into a 5D gravity theory in curved space-time? I didn't fully commit to the bit because I didn't do my Patrick voice, but
why did you when you add this extra dimension? Oh, why did it disconnect? Okay, so
I still hear you.
when you add this extra dimension, how does the strongly coupled goes to weakly coupled gravity? I don't understand that, I guess.
Well, it's because I didn't explain it. So yeah, so that's the whole thing, right? Why would it become weakly coupled in the gravity theory? And there are reasons to believe that have been mathematically proved in a string theory, a particular types of string theory. that where this correspondence is exact. The problem with that string theory is that it describes a particle physics that is not reality. It's similar to reality, but it's, I mean, in that reality, supersymmetry is real for one thing, which it doesn't appear to be real here in this universe. But so we basically say, well, okay, that's mathematically true for this one particular weird case. What if we just fudge it a little bit and see if it works out? So that's my best explanation for why that works. Yeah. So these are excited states of different mesons. So this was my PhD thesis, and you can see my model fits those pretty well. Now that was because I made the model to try and fit those, right? So you kind of use this known relatively easy problem, right? Just looking at the excited states of a quark anti-quark pair to try and constrain your model, and then so this is for then try and make predictions. So here's for glue balls. This is comparing to a prediction from lattice QCD, but you know, if glue balls are discovered and we look at their excited states, you know, we can see how well my prediction matches. We'll skip this. My beautiful animations that take a while to skip through. So we can look at when these particles melt. Yeah, we're running out of time here. But the main thing that I'm working on now, so here's a picture of the phase diagram for ice, water, and steam. We can see that, and this is not something that most of us have direct experience with, at a really high pressure, you know, water going to steam, there's a sharp distinction, right? You know what hot water is compared to steam. They're very different densities. But at a very high pressure, that changeover is much more gradual. And so that ending point is called a critical point. So we go from that discontinuous first order phase transition to something that's smooth like a crossover, which is what we're looking for in the quark gluon plasma. We would expect, so we know it in the low density case, because that's what can be solved with lattice models. We know that that would be a smooth transition, but we expect to be more abrupt at higher density. So that's something that's being looked for in the current experiments, and that's also what I'm trying to reproduce in my model, where that critical point is, at what temperature and at what pressure, or sorry, what temperature, what density would it go from that sort of smooth transition to a really sharp, distinct transition between ordinary nuclear matter and the quark gluon plasma. So we'll leave it there. That's kind of our wrap up for our nuclear particle stuff. You know, I can hang out and answer any more questions, whether about this stuff or anything else. Oh, one thing I want to do. So we have 3 topics left for the semester on the syllabus. We have cosmology, statistical physics, and solid state physics. So I kind of want to order that based on interest. So I'm going to send out a survey and just sort of see what people are most interested in out of those topics, and we'll kind of focus the rest of the semester that way. So any questions, comments, anything?
I have a question.
Yes.
So with the whole satisfactory, unsatisfactory thing, I don't know if this is a question for you or